Hi students, in this video we are going to study about fiber optics. Okay, in the same unit the first chapter is lasers and the second chapter is fiber optics. We already discussed about lasers, so here onwards we are going to discuss about what is fiber optics. We already know the optics means which deals with the light. Now fiber optics means the how the fiber deals with the optics. That means how the light will travel inside a fiber. Okay, let us see what is a fiber optics and what are the basic topics we are discussed in this chapter. Okay, so introduction to optical fiber. So what is optical fiber and what advantages of optical fibers, construction and principle of optical fiber, working an optical fiber, and calculation of numerical aperture and acceptance angle. For this we have a lab experiment also. What is that means? To find out the numerical aperture and acceptance angle for a particular fiber cable, and classification of fibers based on refractive index profile, and attenuation and losses in fibers, applications of fibers in different fields like communications, medical, sensors, and whatever it may be. Okay, so now we are going to discuss about fiber and a small brief introduction. Generally, communication is transferred through carrier waves in any communication system. When the frequency of waves, carrier waves, is high, then information carrying capacity also enhances. Means the best purpose for using the optical fibers is for communication. So in the form of carrier waves, in any communication system, when the frequency of carrier waves is higher, then the information carrying capacity also enhances. In general, the example is if a strength of a man is high, then the working capacity is also high. So like that, the frequency of a carrier waves is high, so the information carrying capacity of waves also enhances. So we know that light propagates in the form of high frequency waves. So light waves can be used to carry information, that is as carrier waves. Carrier waves is nothing but which carries the information. So light waves carries more information than radio and microwaves. So light waves have what is the frequency that carries the light waves, microwaves, radio waves are given here. So highest capacity is for the light waves. And next, let us see what is the optical fiber or fiber optics. For the proper guiding of information carrying light waves, a proper guiding medium is required. That material is optical fiber. So, for the transmission of information, we need a channel. So, what is the channel means? Here is the material. That material is a optical fiber. So for the transmission of information we need a medium. That material medium is a fiber which acts as a channel. And now optical fiber. So optical fiber is a guiding medium for carrying information from one place to another place in the form of light waves. Optical fiber works as a channel in communication. Okay, and next, so we are using the fiber as channel. For those, the channel should possess some special properties. So let us see what are the special properties that the channel should have. It has to allow all frequencies, that is channel should have high bandwidth, it should have minimum transmission losses. That means it should allow any type of frequencies through the channel and should have high bandwidth. For this allowance of frequencies, it should possess a high bandwidth and it should have minimum transmission losses. So by using these fibers, we can't say that the loss is zero, but it is completely negligible loss. So that's why these fibers play major role in nowadays. So these two properties are present in a optical fiber. So it is used in communication as channel. So these two special properties having in the fiber. So we are using this fiber as a channel in our communication system. To guide the light waves, optical fiber should be transparent, and to minimize the transmission losses, the optical fiber should be thin. So it guides the light waves. So the fiber should be a transparent, and to minimize the transmission losses, the optical fiber should be thin. So optical fiber is a very thin, transparent dielectric material which is made up of glass, plastic, silica, like, okay. And now transmission of light along the cylindrical fiber by multiple total internal reflection was first demonstrated by John Tyndall in 1870. So see how the fibers will be, okay. Now, let us see what are the advantages of fibers in communication. High information carrying capacity, an extremely wide band, that means bandwidth is high, smaller diameter, less weight and low cost, longer lifespan, lack of crosstalk between parallel fibers, high temperature resistance, no danger of short circuits. It can be used even in explosive environments, high security for tapping, and immunity to inductive interface. So it protects also the overlapping of signals between parallel fibers, okay. And now, so fibers are more reliable and easy to maintain than copper cables, so we can easily maintain them from thefting also. Flexibility of bandwidth, they possess low transmission losses and noise free transmission. Potential of delivering signals at low cost, because fibers are made up of silica which is available in abundance in nature, okay. So the abundance in nature is a silica is also a material. So these are very easy to maintain, okay. Let us see how the layers that the fiber have means core, cladding, and coating. Coating means silver coating, whatever, that is for a information quality, okay. Fiber core, cladding, coating, tight buffer, strength members, cable jacket, okay. Those are all the protecting layers. The complete phenomena was done in within the fiber core, and the cladding protecting that light only. So let us see construction of optical fiber. One is the core. So the central part is the central cylindrical part which acts as a denser medium. So the light transmits within the core only. And cladding, another cylindrical shell which acts as a rarer medium. It keeps the light within the core only. So the light propagates through the fiber core only, and cladding protects the light and it keeps the light within the core. And next is silica coating, that here we are using a silicon coating. It improves the quality of transmission of light. So for the suitable coating of light we are using for the quality of information which we are traveling through this fiber. And next is a buffer jacket. Buffer jacket is nothing but tight buffer. It protects the fiber from moistures and aberrations. And strength members, it provides necessary toughness and tensile strength to the fiber. And black polyurethane layer or cable jacket, it also protects the fiber from surrounding atmosphere. So all these are which guides and protects the information. So except core, cladding, remaining all named as a protecting layers. So each one is different from their properties. And next, so let us see what is the principle of optical fiber. once light rays enter into the core, they propagate by means of a multiple total internal reflection at the core cladding interface. So whenever the light ray enters into the core medium, the light rays are propagate by means of multiple total internal reflections. That means number of reflections will take place inside the core. That means at the core cladding interface. So that is said to be a multiple total internal reflection. So let us see what is total internal reflection. So total internal reflection means the complete reflection of light ray reaching an interface with a less dense medium when the angle of incidence exceeds the critical angle. So angle of incidence exceeds the critical angle whenever at that angle we are incident a light on the core medium. So then it will takes complete reflections at the core cladding interface. So now let us see what are the conditions to produce this total internal reflection. The light should travel from denser medium to rarer medium. We know that because the core is made up of denser medium and the cladding is a rarer medium. The angle of incidence at core cladding interface should be greater than the critical angle of the medium. So these two conditions are obeyed by this. So it provides the total internal reflection condition. Okay. And next, we are dealing with a critical angle greater than the critical angle greater than the critical angle. Let us see what is the critical angle position and what is the normal incident position and what happens. So we have three conditions, that is I less than theta c, I equal to theta c and I greater than theta c. I is the angle of incidence and theta c is the critical angle. Let us see I less than theta c. Light ray is refracted into the rarer medium. I less than theta c, light ray is refracted into the rarer medium. See, in the first diagram we are taking two mediums, it's a air medium and water medium, and now we are discussing in this. So whenever the incident ray and then how the refracted ray will be. So whenever the angle of incidence I is less than the critical angle, the light ray refracted into the rarer medium. So the air is a rarer medium and the water is a denser medium. So it will refracted to another medium. And I equal to theta c. So light traverses along a core cladding interface, so that angle of refraction is 90 degrees. So whenever the angle of incidence is equal to the critical angle, then the refracted ray will traverses along core cladding interface like that. So the angle of refraction is 90 degrees. So there is no condition of total internal reflection. And next, I greater than theta c means angle of incidence is greater than a critical angle. Light rays totally reflected back into the core and undergoes total internal reflection. Here only we are gaining our required condition. That means the light rays totally reflected back into the same medium, that's into the core region, and that will takes multiple reflection and gives a total internal reflection condition. And now, so let us see what is the working of a optical fiber. So it should not be a straight, right? So the cable should be its possible direction. So in that also the light should take a path like multiple internal reflections. Okay, so we are sending two signals. There's a one light signal 1 and light signal 2. The what is the phenomena is going on this fiber. See, so the light will propagating through this, and inside the core what will happen, and outside the core, that means inside the within the cladding what will happen. Okay, and next, once light ray enter into the core, they propagate by means of multiple total internal reflection because the angle of incidence is greater than critical angle, so that the light rays travel from one end of the fiber to the other end of the fiber is the principle of optical fiber. See, In this particular diagram, what you are observing, the refractive index of core is N1 and the refractive index for cladding is N2. Okay, and next, how the entrance rays will be, how the refracted rays will be. Okay, see here, core, cladding, and what is the acceptance angle condition, how the ray propagation will be inside the core, and here is a condition for N1 greater than N2. Okay, okay, and next, see, a ray of light AO is incident at O on the end face of the core, and this ray makes an angle of incidence theta naught with the axis of the fiber. We are incidenting a ray at the one end of the fiber. Now, this ray is refracted into the core and passes along OB, and it makes an angle of refraction theta 1 with the fiber axis. Here we are also having a principal axis like fiber axis. Now the refracted ray OB is incident on the core cladding interface with an angle of incidence 90 minus theta 1. So with the angle of incidence at core cladding interface is greater than critical angle, then the ray suffers total internal reflections at the core cladding interface. Okay, whenever I greater than C, the critical angle condition will obey and it possesses total internal reflection condition. Okay, so when the angle of incidence at core cladding interface is greater than the critical angle, then the ray suffers to total internal reflection and that takes multiple reflections inside the fiber. So it is possible if the angle of incidence for a ray at the end face is less than theta naught, then the angle of refraction is less than theta 1 and the angle of incidence at the core cladding interface is larger than critical angle. So the light is totally reflected back into the core medium. So whenever it possible means the angle of incidence at the end face is less than the theta naught. Okay, and then angle of refraction is less than the theta 1 and the angle of incidence at a core cladding interface as larger than a critical angle, so then it totally reflects inside the core medium. So total internal reflection is possible if the angle of incidence at the end face of fiber is less than or equal to theta naught. So at these conditions, the total internal reflection is possible. So this angle of incidence is known as acceptance angle. Okay. And next, let us see what is the acceptance angle and how the numerical aperture will be calculated. Okay. Now, acceptance angle. It is the maximum angle of incidence at the end face of an optical fiber for which the ray can be propagated inside the fiber. That means it's the maximum angle of incidence at the one end of the fiber for which the ray propagated in the optical fiber. So for this angle, the light should propagate that takes multiple reflections within the fiber. So the acceptance angle can be calculated by applying Snell's law at points O and B. So Snell's law at point O, that is at the origin, at the starting point of the ray. So n naught sine theta naught equals to n1 sine theta 1. So sine theta naught equals to n1 by n naught sine theta 1. Let it be equation 1. And now Snell's law at point B. There is also a two medium. So n1 sine 90 minus theta, theta 1, that equals to n2 sine 90 degrees. So n1 sine 90 minus theta, that becomes cos theta. So n1 cos theta 1 equals to n2 and sine 90, that value becomes 1. Okay, and next, so cos theta 1 equals to n2 by n1. So let it be 2. We know that sine theta 1 equals to root of 1 minus cos square theta 1. So that equals to root of 1 minus n2 square by n1 square. So now we are substituting this equation 1. So this equation in equation 1. So sine theta naught equals to n1 by n naught root of 1 minus n2 square by n1 square. So from this equation we are getting, so n1 gets cancelled and root of, so theta naught equals to sine inverse of n1 square minus n2 square by n naught. Okay, so for air, n naught, that equals to 1. The refractive index of air should be n naught, so that it be the value of refractive index of air equals to 1. So theta naught equals to sine inverse of root of n1 square minus n2 square. This is the equation for acceptance angle for a optical fiber. Okay, and then numerical aperture. The numerical aperture represents the light gathering capacity of an optical fiber. So light gathering capacity is proportional to the acceptance angle. So numerical aperture can be represented by the sine of acceptance angle, that is Na equal to sine theta 0. So Na equals to sine inverse of root of n1 square minus n2 square. So Na equals to root of n1 square minus n2 square. So fractional change in this refractive index, that is a ratio between the differences in refractive indices of core and cladding to the refractive index of core. So we are taking the difference, the ratio between core cladding and only at the core medium. So from this we are solving, we are getting an equation that becomes Na equals to root of n1 square minus n2 square. We can write it as a plus b into a minus b, and the a minus b value becomes delta n1. Okay, since n1 is nearly equals to n2, then we are considering as both n1 equals to n2. So numerical aperture can be increased by increasing delta, and thus enhances the light gathering capacity of a fiber. Okay, so and now we are discussing about critical angle. Let us see what is the critical angle means. It is the angle of incidence that provides an angle of refraction of 90 degrees. That means whenever the angle of incidence that provides the refraction angle at 90 degrees, then it is said to be a critical angle. Whenever I greater than theta c, and means angle of incidence is greater than the critical angle, we are getting the total internal reflection condition. So n1 sine 90 minus theta 1 equals to n2 sine 90. So n1 sine, so sine 90, that is a sine theta c. So 90 minus theta 1, that becomes theta c. Okay, so sine theta c equals to n2 by n1. Theta c becomes sine inverse of n2 minus n1. Okay, and next, so simply this is up to numerical aperture and acceptance angle of the fiber. So remaining we will discuss in our next video.